Hello, in this video we're going to continue our solutions to the set of problems that we introduced a couple videos back, reviewing several different applications of derivatives. So we're up to number 7 here. Problem 7, it says a farmer has 670 meters of fencing with which to enclose a rectangular pen adjacent to a long existing wall. He will use the wall for one side of the pen and available fencing for the remaining 3 sides. What is the maximum area that can be enclosed this way? So drawing a picture, we see the wall on the top, which is not fenced. We see a side here of length x, and this is also x. And the total, and this is y here, but x plus 2x plus y is 670. So we see that y is 670 minus 2x. A is the area. Area is x times y, or x times 670 minus 2x. Distributing there, we get the area as a function of x is 670x minus 2x squared. If we want to maximize that area, we want to find the critical point, we take the derivative and set it equal to 0. Taking the derivative of that is just 670 minus 4x. Set that equal to 0. We can then solve for x by adding 4x to both sides, dividing by 4, and we get 167.5. So, and then y turns out to be, well, twice that, 335. So you end up using half of your material for this long side, and the other half is split in half here and here. So the area is maximized at that point. Length times, then you do the x times y, you get this number here. So it turns out that the area is maximized when the fence pieces touching the wall are 167.5 meters long, and the side parallel to the wall is 335 meters long. And with these dimensions, the maximum area is 56,112.5 square meters. The height of a ball, y, is tossed straight up is given by the following formula. Y equals negative 16t squared plus 35t plus 15, where the height is measured in feet and t is the time since the release of the ball measured in seconds. Negative represents the downward direction. Include units on all answers. At what height was the ball released or thrown? That's just y of 0. That's going to be the coefficient, the constant term there, which is 15. So 15 feet above the ground is the height of the ball when it was released at time 0. What's the height of the ball 1 second later? You put in t as 1, and that works out to be, you see the details worked out there, that turns out to be 34 feet above the ground. So notice that it was definitely thrown upward, and then at some point it reaches a maximum height and comes back down. Eventually will land on the ground. The velocity is the instantaneous rate of change in the height with respect to time. What's the velocity formula as a function of time? Well, it's just the derivative of the height. So v of t is y prime of t, and that's just negative 32 t plus 35 by doing the derivative of this function here. At what speed was the ball thrown? That's just v of 0, which is 35 feet per second upward, since it's positive, so it was thrown upward at that speed. What is the velocity of the ball 1 second after release? You plug in t as 1 here, and note it is still moving upward at 3 feet per second 1 second after release. So it was thrown upward pretty hard, so that 1 second after release it's still going upward, although a lot slower than what it was. When is the ball at a maximum height? Well, we want the velocity to be 0 at the maximum height. In other words, the derivative to be, of the original function to be 0. So plug that 0 there and solve for t. Let's see, add 32t to both sides, divide by 32. So t is 35 over 32, or exactly 1.09375 seconds after release. Okay, so at 1 second it was pretty close to its top thing, just a little bit after that. 3/32 of a second later, it's at its maximum height. What is that maximum height? that should say not of 1, but of 35 over 32. There we go. It's y of that particular t value, which is what I have worked out here. I did it on a calculator. Worked it out here is exactly this. This is also exact in decimals. 34.140625 feet above the ground. The acceleration of the ball is the instantaneous rate of change of velocity. What's that? Acceleration. Well, that's the derivative of the velocity function. Where's the velocity function? Right. There it is. Take the derivative of that. It's a constant negative 32 feet per second. This acceleration is constant. This is realistic because this is the acceleration for any object near the surface of the Earth. The acceleration is practically constant, and that is the correct constant for it if the air resistance is not a factor, which it probably wouldn't be on a pretty compact ball. If this was something that was a feather, this wouldn't work on. When does the ball reach the ground? Well, it reaches the ground when y is 0. Velocity is definitely not 0, but the height is 0. So there's the height function right there. Plug in 0 for y and solve for t. That's a quadratic polynomial equation, so we use the quadratic formula on it, which you can see here. Hopefully you remember how to do that. And you can see the details worked out there. So there's sort of an exact value. The negative 1 doesn't apply because it gives you a negative answer. It's not because time didn't exist before we let go of the ball, but these equations don't apply before that. So the time values that are appropriate are from t equals 0 up until the ball hits the ground. And it's about 2.55 seconds after it was released. So this is valid for about 0 to 2.55 seconds. So in the last video, we analyzed a family of functions. This time we're going to analyze a specific function. F of x equals the natural logarithm of parentheses x cubed plus 1. I didn't really have to say x is greater than negative 1. That's implied by this because x cubed plus 1 has to be positive because the logarithm is only defined for positive values. And so that happens when x is greater than negative 1. So describe the behavior, what was so-called end behavior, as x approaches infinity and on the right, and on the left it's approaching negative 1 from the right side. So as x approaches negative 1 from the right side, the u here is approaching 0 from the right side. And we know the log of u approaches negative infinity as u approaches 0 from the right side. So as x approaches negative 1 from the right, the graph of f of x has a vertical asymptote of x equals negative 1 pointing downward, and the function is undefined for x less than or equal to negative 1. As x approaches infinity, u equals x cubed plus 1 also is approaching infinity, and we know that natural log of u approaches infinity as u approaches infinity. So the graph is going to increase without bound as it goes to the extreme right. However, it will grow at approximately the same rate as log of x cubed, which is 3 log of x. So it's going to be growing along the same rate as a logarithm function does, which is slower and slower as it goes farther and farther to the right, but not an asymptote. It does go on up forever. And we can kind of confirm this a little bit with this first and second derivatives. When is the value of the x? What values of x is the function increasing? When is it decreasing? Well, we need to look at the derivative for that. So we need to take the derivative of log of s. So that's log of u. So the derivative of that's 1 over u times the derivative of the u. The derivative of the inside is 3x squared. So our derivative is 3x squared over x cubed plus 1. We want that to be positive if the function is going to be increasing. And so anytime the x, let's see, well, the x squared is going to be positive or 0 no matter what. 3 times that's still positive or 0. So it's going to be positive when the denominator is positive, and that's going to be anything greater than -1, except the top is 0 here when x is 0. So it'll go from -1 to infinity except for 0. In other words, you could say from -1 to 0 and then from 0 to infinity. And f prime of 0 is 0. So the function is actually increasing from -1 to infinity. There is a stationary point at 0, 0 with a horizontal tangent line, but it's still actually increasing through that point. So it actually turns out to be an inflection point there. There are no local extrema. There's no place. The only place the derivative is 0 is here, and we'll see in a minute. That actually turns out to be an inflection point, not a minimum or maximum. A second derivative is the derivative of this rational function here, the derivative of the first derivative. So we take that, bring it down here. Do the quotient rule here, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. Let's see, the derivative of the bottom is 3x squared. It goes here at the end. This one right here is the 6x is the derivative of the top here. So distribute here, that's 6x to the fourth plus 6x. Then we got minus 9x to the fourth, put our combined like terms, that's negative 3x to the fourth plus 6x there. And factor out a negative 3x, and we get negative 3x times x cubed minus 2 over x cubed plus 1 squared. When is the second derivative equal to 0? Well, that's when the top is equal to 0. That happens when x is 0. And like we already said, there's an inflection point there. Notice when the derivative, first and second derivatives are 0, it could be possibly an inflection point or an extremum. It turns out in this case it's an inflection point. And if you do x cubed minus 2 is the other, could be 0 is the other possibility, and that's x is 2 to the 1/3 or the cube root of 2. If you do f of 0, you get 1 for the original function. You get log of 1, which is 0 for the original function. That's the origin. So the origin is there. And let's see. And so of course that's the y-intercept, right? And the only x-intercept as well. And if you do f of 2 to the 1/3 power, you get well, you're going to cube this, and the 1/3 cancel out, so you get 2 plus 1 is 3. So you get natural log of 3 there. So that point, cube root of 2 comma log of 3, is an inflection point. And so it turns out the graph is concave down where the second derivative is negative. Well, when is that going to happen? Well, that's going to happen between -1 and 0. Between -1 and 0, this is squared, so this is positive no matter what. So you just have to look at this. Between -1 and 0, these are, let's see, that's negative, so that's positive. And then we have a negative here, so that's 3 negatives in the top multiplied together is negative. And so that's concave down. Greater than from 2 1/3 up, bigger than 2 to the 1/3, this term is positive. This is positive, so that makes the whole top negative. The bottom is always positive. So that makes the derivative, second derivative, negative whenever you're in there. Between 0 and 1, or between 0 and 2 to the 1/3, then this term right here, x cubed minus 2, is negative, but the x is positive, so the top turns out to be all positive. Bottom's always positive because of the square, and you get a concave up for that portion. So there are two inflection points, 0, 0, and 2 to the 1/3 comma natural log of 3, or approximately this. And you can see it here. I've marked the two inflection points with red dots. One's at the origin, one's here, but actually this function increases forever. So you got this nice little vertical asymptote here, increasing concave down to the origin, horizontal tangent line there, as well as being an inflection point there, as well as crossing both axes. Then it's increasing concave up for a while to this inflection point right here. And then from there on, it's increasing concave down, but it doesn't have an asymptote. It still goes on up forever there. So the range is all real numbers, actually. and the domain is from 1 to -1 to infinity, not including -1.